When homologous chromosomes pair up in metaphase 1 of meiosis, the chromosomes inherited from the father and from the mother line up randomly on either side of the cell's equator. This model cell has two pairs of homologous chromosomes. This assortment of chromosomes is a matter of chance. The arrangement of any one homologous pair does not depend on the arrangement of any other homologous pair. Therefore, it is referred to as independent assortment. In anaphase 1, the paired homologous chromosomes separate from each other and move toward opposite sides of the cell. Finally, the cell undergoes cytokinesis, forming two genetically unique cells. As meiosis II begins, the nuclear membrane breaks down, and centrioles move to opposite sides of the cell. Spindle fibers align the chromosomes at the cell equator. The sister chromatids are pulled apart from each other and move to opposite sides of the cell. The gametes formed contain two different combinations of chromosomes. Now, let's see what happens when the pairs of homologous chromosomes align differently at the cell's equator. In a cell with two sets of homologous chromosomes, 4 combinations of chromosomes are possible. Therefore, the gametes produced by meiosis are not genetically identical. This variety is a source of genetic variation. Let's look at a cell with 3 sets of homologous chromosomes. How many chromosome combinations do you think are possible this time? The more sets of chromosomes a cell contains, the more possible combinations of chromosomes there can be in the resulting gametes. A cell with 3 pairs of homologous chromosomes can produce gametes with 8 possible combinations of chromosomes. A formula can be used to determine the number of possible chromosome combinations. 2 to the n, where n is the number of pairs of homologous chromosomes. As you can see, the more chromosomes there are in a cell, the more possible combinations of chromosomes there are. For this reason, independent assortment during meiosis is a major contributor to genetic variation.